As you can see, this formulation provides a relation between the applied torque and the internal shear stresses. But it does not tell us anything about the distribution of shear stresses within the material. Meaning all about the inside of material and the behavior by the action of different forces. To get an inside view of a material, let's consider another shot.
Let's look at this diagram. A. There are two different triangles ABA dash and AOA dash. Taking tangent of both triangles formed on the diagram, we say that tan gamma equal to AA dash over L for triangle ABA dash, and tan phi equal to AA dash over rho. For a small triangle's tangent of any angle is equal to the angle itself. So gamma equal to AA dash over L and phi equal to AA dash over rho. Selecting AA dash as the subject, and by comparing both equations we get gamma L equal to rho phi, or phi equal to gamma L over rho, where gamma is the shear strain and is the measure of angular deformation in the rod being subjected to any angular loading. Whenever there is shear stress present inside the material, they causes the shear strain. We can relate them together by the help of property called modulus of rigidity, which is the property of material to resist any angular deformation. Thus, gamma g equal to tau. Substituting the value of gamma in the above equation, we get a relation between the torque applied and the angle of twist. Phi rho over L equal to gamma. Relating equation 1 and 3, we get integral of rho gamma over g dA, or integral of rho phi rho over g L dA. Rearranging the equation and taking the constants out of the integral, we get phi over g L rho square dA, where the quantity inside the integral is known as the polar moment of area and is represented by J, which is the resistance of the material to rotate. So T equal to J phi over GL.
This was some little introduction of the torsion. Now we will drive ourselves to some practical examples of torsion and the use of
A structure is a group of elements somehow united to support a load with stability. Examples of structures are bridges, electricity pylons, or dams. Can you think of others? Well, you will probably think of tall buildings or long bridges, but there are also other examples such as chairs or tables that we use every day. Even an egg has a structure. This is an image of modern skyscraper with two main structures: a skeleton or frame made of steel, and the skin of the skyscraper is the walls that are made of glass panels and thin concrete sheets. All structures must be capable of withstanding the loads and forces for which they are designed. This does not, however, mean they must be always rigid. Some structures are designed to be flexible, and they are often more withstand dynamic forces. These forces, which they change direction and quickly become more intense. Buildings such as those built in the region of the earthquake. The wind coming from the top side of the building provides a rotation to the building, and in result to that the building gets twisted. This twisting force must be counted during the designing. The main reason is to attract the people towards luxury, and every engineer wants to be the smarter and show the best of what they have got. But if we speak in technical manner, in most of the mountain areas and desert areas, or anywhere where there are not enough spaces or the good basis to build horizontally, we choose to go vertically upward.
while working, these shafts are always in torsion.
intensity of which depends upon the workload and the driving conditions. While designing, the optimum conditions of shaft are taken into account with some factor of safety. Behind me is a submarine. Like all marine vehicles, including submarines, engine power is transmitted to the propeller through these giant shafts. Due to the viscosity of water, a drag force is experienced by the propeller, which counters the provided engine torque. Thus, the shaft is under intense torsional loading, and shear stresses are generated within it that must be incorporated during the calculation to make it safe.